My name is Katherine Riley. I'm the Director of Science for the Argonne Leadership Computing Facility. And I'm going to talk today a little bit. My talk is meant to be more motivation, very high level about what we're going to be talking about today, which is really scientific software practice and good best practices to use when you're developing your scientific applications. And so before I get into any of it, I generally have a question. By your own definition, because I'm not going to lead in with a definition, I'm curious, how many here think they are working with applications where there is some degree of best practices, of engineering practices going on with what you're working on? So just to raise a hands. This is awesome. And so you don't feel alone, because I want to ask the other side too. Those of you who are walking into situations or maybe confronted in your own development, right? And you don't have any right now, or you're in a group that doesn't want to do it. Is there anybody in that category here today? Okay, awesome. Just know you're really not alone. And I'll get into that a little bit, right? I think contextually for the scientific community, really, why you're not alone. But the other reason I asked that question at the very beginning is I want to point something out, that when I've been doing this for about 25 years. I can tell you that the people raising their hands in the first question of yes, we have a practice 25 years ago was almost nobody. There were some people, if you worked at the NNSA labs in the United States, who might have raised their hands, and a few unique others, but by far, almost nobody would have raised their hands. And I would argue that even when we started this training program, not even argue, I would state as fact, when we started this training program, almost nobody raised their hands. There were a few who raised their hands, and very, very few. It was really the complete binary flip of what we just saw right now. And there's a few kind of exciting reasons for that. I would argue exciting, some would argue frustrating, which is that our scientific world and our computing world is getting more complex and hard very quickly. And so it's driving more people to think about that. But I also think it's also just awareness, right, of how you develop software. And people are thinking about it more than we were when I was getting trained. In the 90s, that just, no, just write your code and be done with it and go away, was kind of the mindset of how I was trained originally. And so this is what we're going to talk about today, though. And the idea of today is to not give you some prescription, not to say, go do this, you have to do it this way. That's not the point. The point is to talk about why some ideas of scientific practice are important and how you might fold them in. I'm going to really encourage you, for the speakers you have today, challenge them, ask them questions about really how they've been doing this, how they've introduced these to different groups, and the challenges they face in doing them, or how they've customized them in the different groups they have. All of these people have been doing this for a long time, actually the engineering side of this. So have a good sense of how do you customize this? How do you make this work for my particular group? So dig into them for that, right? Because that's actually what you should walk away from today with, is how can I make this work for me? How can I save my time? Okay. All right. I also, by the way, talk quickly, especially in the morning when I've been drinking coffee on the 45-minute drive up here. So feel free to stop me. Feel free to ask questions. And also feel free to challenge me. I mean, I want you to challenge Anshu later as much as you can, and Jared as much as you can later, but feel free to call me out on anything or bring stuff up. Okay, random license and citation slide that I need to have. And so this is, I think, in the end, the whole day in 2 points. And I'll tell you, I really care about this, right? So as a director of science for a facility, and I've been doing this, running the facility for 15 years, and primarily being concerned about the science output of a national user facility, I really care that the people who get time on our resources, time that's worth a lot of money and people time, get good results, that get reliable results, that get impactful results. So I'm going to tell you straight up, and I would probably not even budge on it, that good scientific good scientific practice, like practicing the scientific method properly, requires good software practices. And this is understood in the experimental community, I would argue. I mean, nobody's perfect, right? But the experimental community does this. The computational science side has had a historic problem with it. And as we can see, it's getting better. But you need this. It's absolutely crucial. But the bonus side, if better science isn't a good motivator for you, and I hope it is that good software practices, frankly, will also save your time, right? It will give you better productivity. You will be able to ask more questions, more interesting questions. You'll be able to move more dexterously. You will be able to be more successful if you have good software practices. Okay. And so that's the short version of why I want everybody to care. Sort of the larger version of why I want people to care, more dramatically, switching, is that we know that mistakes happen. Even when people really, really don't want mistakes to happen, right? So, you can Google the most famous engineering mistakes of the world, and there are a lot of really interesting ones. The Challenger is one that's particularly personal to me, right? Just mostly because I remember watching it in my 6th grade science class. And I think it's also an interesting one because the consequences of that, besides the loss of life, were really dramatic. Right? And this is one that if you've taken actually classes in problem solving and in communication and in management, this is one that comes up a lot. Because it has to do with not only the mistakes that happened, but the communication failures that happened. And while you might be thinking of, yeah, but that's NASA building a space shuttle and there were politics involved, and there were, this exact thing happens in science groups all the time. And I'll bring it back to sort of some more real world examples in a little bit. And Chernobyl also, I always leave this one up here because not only is it very dramatic and another good example of just a lot of failure to communicate and some politics, it's also very personal to me because we were living in Belgium until about a month before this happened. And so I'm kind of happy we moved when we did. But there's other categories of engineering and software mistakes that you see on a day-to-day basis. They happen everywhere. And the U2K one is a really, I think, and also an interesting one that I will come back to multiple times in this talk. And I'm not really sure how many people here may be old enough to actually remember when we went from 1999 to 2000. But the 2-second version of this, right, is that for the better part of 50 years of software development, nobody had thought to think that we were going to change a millennium. They didn't. And so all the year representations in there were XX, 74. And so we were looking at a situation in financial software, human resource software, every bit of software basically people were interacting with where we were going to transition from the year 1999 to the year 1900. And that was going to break a lot of things. I was also kind of interesting to watch, right, as the doomsday scenario sort of also percolated up from this. And that was fine, right? But this was an interesting example that's even more relevant to scientific software about the assumption of the lifetime of your code. And boy, I'll come back to that one. Mostly, I'll come back to it and keep saying over and over again, it will live longer than you ever think it will. But this is also a good example of technical debt, which is a term I'll define later. And in some cases, people being aware of the assumptions that they were making, and in some cases, people really not being aware of the implications of the assumptions that they were making. And I'm choosing very big examples here, so people at least can sort of, remember maybe some of these happening, although occasionally it occurs to me that all of my examples predate the 2000s, and I'm just getting older, and the audience is pretty much staying normally about the same age when I'm talking about these things. So I got to get some more recent ones. But I like this one a lot. So this for those who are not familiar with it, is the Mars Climate Orbiter. And in the late 1900s, the Mars Climate Orbiter was lost by NASA. And so the Climate Orbiter's job was to take orbit around Mars to communicate with the polar lander, to actually help just communicate information, as I lose my hair. And the short version of what happened was a units issue. The ground unit and the orbiter were representing calculations in different units, and so the orbiter was lost. And I think we're all very smart and have some sense of just the scale of loss. It's one thing to put a satellite in orbit and lose it. It's another one to build a satellite, send it to Mars, try to get it into orbit and lose it, right? That was a huge loss due to a lack of communication within a team. A large team, but still a team. And what I encourage you guys to think about, right, is if your research group is 5 people, or if your research group is 30 people distributed across countries, you all have teams, whether they're formal or not. You all have people who are doing different things, right? And these communications within teams are really important to avoid assumptions like this. I will tell you, I know personally of examples where this has happened in applications multiple times, resulting in people having to actually withdraw publications and retract results, right? So this is a real thing that happens. And to touch back to something I said before, right? The reason I care is because I run a big facility where hopefully, many of you will get time to run large-scale science of some sort, right? That's the job, right? That's the reason we build these facilities, is we want high-impact, really sort of exciting science to run on these big computers. But what often also gets lost, I'm going to go back to pointing to experimentalists versus people doing computational science, and there is an overlap. It's not that hard split, but many people consider the cost when they're doing something like allocating time on an experimental resource. If people are getting time at LHC or the Advanced Photon Source at Argonne or SLAC in California, they're considering how much did that resource cost to build, how much is my time on the beam worth. They often don't do that equivalent, right, on a supercomputer. And there's a lot of historical reasons for it and weird bits of psychology that I'm not going to pretend to dive into too much, but they don't, and I know they don't. So I want to encourage you guys to realize, right, that comparatively, while LHC was really, really expensive to build and maintain, overall, given the life of LHC, it's not particularly more expensive to get a shot at LHC than it is to get, a 3-year allocation on one of these supercomputers. And it's just the way the costs balance out. They're expensive. They're real. Now, I don't want people to be obsessed about the dollar amount of the award they get, but I want people to understand that there's a real cost associated with using these resources, that they're expensive, that they're not free. And this is relevant not only to making sure you plan out your time well and think about how hard it is to get an allocation on a large-scale resource, but also thinking about it in terms of the productivity of your software, right? And do you want to fight really hard? I tend to use very aggressive language, but compete very hard to get an award on a resource, and then lose perhaps half of it because you realize there was an error halfway through your allocation, and have to fight again to get another award. Think about it from these perspectives. That maybe sounds scarier than I want it to sound, but I do try to instill in people a respect for the scale of the compute resources that the Department of Energy anyway builds, and the amount of time, the value of the time that you get on it. All right. So what I'm also going to do before I sort of get into the larger overview of what people are going to touch on today is actually acknowledge that no matter how many good practices you evoke in your process, mistakes happen. And they happen for all kinds of reasons, and sometimes it's even the larger cultural model of how science operates, today at least. So this is a very personal example because this was an application that I worked for many years on. This was a campaign that was run by people who I respect the heck out of, who have driven home to the larger community how to use good software practice, right? And who are very careful about their software practices. But what happened was, this is an older example, so meaning that this was not in the past few years, but they got a call, basically it said, hey, do you want a week and a half just devoted time on one of the biggest resources in the world at that point? And this was a blue gene at Lawrence Livermore. And for those who are not familiar with it, this is not necessarily reproducible. You occasionally get these calls, this team would occasionally get these calls from the NNSA labs. And it was sort of like, you can do it now or you cannot do it at all because we're going to flip the switch. It's going to go into the high security section and you won't get a chance again. And so they had the decision about whether they wanted to do this, but they had less than a month to get ready, and the simulation that they wanted to run needed a new capability implemented in the code. A code that had really good developmental practices and testing, very rigorous testing practices. And to cut to the short of it, they did this, but after they did the run, by all immediate observations successfully, it became clear that the quick and dirty implementation of particles that they had done had an error. And basically, of the billions of particles that they were trying to track, or the millions of particles they were trying to track, particles had the same tag. So particles got lost. 5 particles looked like the same particle if you tried to look up. And so this week and a half worth of effort that they could not reproduce because they couldn't get that time again took 6 months to post-process in order to recover that data and able to actually move forward with the original science question that they had with it. But this was a project that had good scientific process and good scientific practices in place. But they kind of put a halt to some of those by necessity, right? Because the call of, hey, you have a month, less than a month, to develop this new capability, prepare the science properly to do this run, and go. Can you do it? And so I bring this up as kind of a complicated comment, right? It's to say that we recognize that just life happens, right? And opportunities happen, and sometimes you just got to go. But the whole reason to have practices in place is to minimize the chance that something like this will happen. And you'll never go to zero. It's kind of like safety, and if anybody's ever been confronted with this, you'll understand it, right? Like in safety practice, whether it's at a university or a national lab or at a business, right? We must have 0 accidents ever, ignoring what kind of the definition of an accident is, right? You're going to have an accident by definition. But the idea of implementing good safety protocols, right, is that you'll minimize them. You will have fewer of them. And so mostly, as I said, I wanted to bring out that even with good practices, stuff happens. But this is a real example of it. Okay, I already touched on most of this, right? But the objectives of what we want to talk about today. The primary one is to bring knowledge of what we have found through at this point, nearing in on 2 to 3 decades of experience for the material you'll see today, even a little bit more depending on your perspective. What has really been effective in scientific teams for good software practices, and ideas about how you might implement them and ways to customize them. It's not meant to be prescriptive. And again, as I point out, this customization is, I think, one of the key parts. Understanding and getting some clues about how you might make that work for your team of 2 versus your team of 10 versus your team of 30. How you might make that work for a really simple code with 2 developers or a really complicated code with 10 developers. And thinking about how you want to do it. But with all of these things, keeping in mind that any code, it's not even your code, any code is going to live a lot longer than anybody thinks it will. Even that quick and dirty thing that you threw together at 1 in the morning and you promised yourself that next week you were going to go and fix it, it's probably not going to be done a week later, right? It's going to live longer than you think it will. And that your science campaigns have real people costs, have real straight up costs, right? So value those, think about those. The practices are ways to value those costs and reduce them, actually. So in terms of productivity. All right, I won't worry so much about the agenda, but what basically after me, it's going to be a sort of a breakdown in very specific topics, these topics that we have found to be most productive for projects to develop. Okay, so this is kind of jumping right back into the Flash comment before. So the Flash anecdote earlier. The Flash anecdote was, with the particles in the air, is really a good example of what is often referred to as a heroic effort, heroic programming. It is not necessarily a good term when it's used in these contexts. It is really used to refer to having to put exceedingly large amounts of effort by individuals or an individual to overcome some failure in the process. Now that could be project planning, right? Or it could be the fact that there is no planning, right? You get a call that says, hey, you have this huge opportunity in a month. You want to do it? There's only so much planning you can do for that, right? Especially if you have no idea that it might come around. But other components, can contribute to this too, like failures to communicate within a team, failures to have, rules about how you want to develop, whatever. But the other thing that I want to point out about this idea of heroic programming is that it's really familiar to, I think, most people in the scientific community. It might not have programming after it. It might have, heroic thesis writing or whatever, right? That's how science operates in many respects, right? It's like by these sprints of heroic effort. So as a result, I will say that few people think about this and go, well, yeah, that's how we do it. There's no problem with that. Few people look at this and see a problem with it. And I'm going to describe why I think there is a problem with it going forward. But this is why it's so common in application development, scientific application development, I would argue, is that We all know this model because we've all survived it and we've all operated in it, and that's just the way science works. Oh, there's a duplicated slide. All right, and it's really that, oh, I see, it's not the duplicated slide, I'm just not paying attention. It's that really science teams don't recognize this because it's so similar to how we normally operate. So this is what happens when I leave a slide in PowerPoint mode the entire time. I never practice and remind myself that I have this animation in here. And this has happened like actually many times I've given this talk. I don't like the incremental appearance of things. So what's wrong with heroic programming? And here I am going to zoom in specifically into how we're developing applications, how we think about scientific code development as a larger community. I would argue that 20 years ago, heroic programming development was more viable. When I was starting and staring at codes 25 years ago and staring at computers 25 years ago, I'm not saying they were trivial and that the applications were trivial, but it was much easier for me to have full grasp on what that computer was doing and a full grasp on what that code was doing, because just by the scale of the systems at the time. Within about 10 years into my career, that got trickier. And I was also sort of trying to work in groups that were pushing both the science and the scale of the systems that were available at the time. And I would say that today it is incredibly difficult to have a single person or a very, very small number of people, like 1 or 2 people, be able to have such a good comprehension of both everything an application is doing from the physical model, right? Like starting with your science question all the way down to the performance and the numerics and what the system is doing. That heroic programming becomes incredibly difficult to sustainably do as a way to solve a problem. Okay, unwinding that a little bit more. Part of that is because our science questions are more interesting, are more complicated, right? We're at, it's that process of science, right? You ask the question right in front of you and you get 20 more as a result. And you're going to develop a code that's going to help you tackle those next 20 questions. And so codes today don't really look simpler than they did 20 years ago because the fidelity of your models is increasing, or the complexity, how much physics you're incorporating into it. The multi-scale physics is there. That people were just like, nope, I can't even consider that. I can't even potentially consider doing that computationally. So first, we have more understanding of science, more questions we're trying to ask. That's making the codes more complicated. But then also, yeah, we're making the computers harder, just straight up. I have whole talks about this one where we're not actually trying to make the computers harder. We're really not. But they are getting more complex, and part of that's just the advance of technology. Some cases it's the failure of technology to move fast enough, but some cases it's just genuinely the advance of technology and the scale of these things. The computers are challenging, and we don't necessarily have a software stack that even makes it easier to understand, right? So it's possible in the utopian world where we have an absolutely perfect software stack where somebody can go away and write a whole science code in a week, that this conversation would be different, but we are not there. We are not there. We don't have the software stack to make that so easy. So the challenge here with heroic programming is you've got such complexity that it is incredibly difficult for a team to sort of suddenly go and spend 2 weeks or a month of heroic effort and not make some huge mistakes that could really cost a lot more than even 6 months of post-processing. But that also the complexity of the problems might not even permit it, right, at all. And this is just a summary in terms of your own slide set that you'll have for reference later, that this is just a summary of the points that I'm sort of talking about. So in extreme scale or exascale science and beyond exascale, I would argue that the complexity of these systems and the complexity of the science problems is just growing. And so consider that it's more difficult to work on a piece of software, right? And work on different components of that as an expert that can really move quickly and deftly and agilely through all of those in a very, very fast rate. Okay. The other component of this is that systems are also changing fast. So I'll talk about this idea of technical debt. And I'll define that in just a second, but lead into it with the following, right? So if you decide to mitigate the complexity of your environment by saying, all right, one of the things I'm going to do is I'm just not going to worry about like using 2 machines. I'm just not going to worry about it. I'm all in on machine X, and I'm going to go just on machine X. The problem is, in 2 years, machine X disappears, and there's no follow-on to machine X. There's no obvious way that you can continue with the way your application has been written. So you reduce the complexity, right, to maybe improve your productivity or to improve your ability to be very agile or to improve your ability to have, like, the postdoc be super heroic for, and get something done and very quickly. But you have a big technical debt because you've assumed that I'm going to stay on machine X, and I've written my code for machine X. I've optimized my code for a particular machine, a particular architecture, and now that machine is gone. I mean, a good example of this right now is that many cores are just gone. You're not going to see that on the large-scale systems, perhaps ever again. I'm not going to say never because, dude, inevitably, right, that'll bring it back in about 5 years. But right now, all of the paths for architecture, right, are accelerator-driven. Both for exascale and post-exascale all have these accelerator-driven models behind them. But a lot of people went all in, and even when confronted with, you maybe should be thinking about how you want to write your code and create abstractions in your code that would allow you to use an accelerator, they just said, no, I can't right now. And it's not a judgment of them that they said, no, I can't right now. But now they have the technical debt of going back and thinking about, well, how can I use an accelerator-based machine? Any flavor of accelerator-based machine, it doesn't really matter, any flavor. The technical debt is really the consequences of the choices that you make in your application. If you've decided that I don't have time right now, I can't validate this particular unit or this particular physics module that I've just developed, I can't do it, you have technical debt. Now, especially in that case, I really hope you go back and resolve that technical debt soon. but acknowledging when you make a choice in your application development, in your software development, that could have consequences for your science, or for your productivity is really a valuable practice. Just writing it down, documenting it somewhere that other people can see. I mean, not necessarily putting it like in big blinky letters, right, on your website. I'm not talking about that, but if you have group documentation or a group Slack channel, like the to-dos, documenting it somewhere like that is really important because it gives you a sense of the assumptions that you've made in your scientific code. Of the real-world example of this is really the year 2K bug. Now, it's really possible that some financial institutions absolutely acknowledged their debt when they wrote that and said, I do not acknowledge that we'll ever change Millennium in this software, and we're just going to stay in the 1900s forever, and we'll have to deal with that later. So I am sure that some companies did not, that some software just completely didn't even consider it as a possibility. But that is a concrete technical debt. It's not necessarily an error. It's an assumption to simplify what you're doing. Those are important to make sometimes. They're necessary to make sometimes. Sometimes you have to suspend practices because you've got a month to prepare for a big campaign that you were given, no warning might happen. But write down those assumptions. Managing your technical debt is one of the most important practices you can have for developing any software. It is the same thing as what you do in thinking about your scientific questions. It's what assumptions do I have here? The assumption that I'm going to stay on the same kind of architecture. The assumption that I'm always going to be writing code for MPI. The assumption that this is actually a correct unit right now, and I can't do better verification on it right now. I'll come back to it. Write those down. Okay, switching. I want to switch gears for a little bit because I've harped on mistakes happen and think about how you're writing your code and think about the mistakes that might happen in your code. And it's all very technical. And I kind of gloss over, I haven't even touched on it. Not that I've glossed over. I'm trying not to gloss over it. One of the biggest challenges today, and one of the biggest challenges certainly for the past several decades has been when it comes to developing scientific software. The short version of this is that universities especially don't tend to value it. Where do you get your academic credentials for it? So this quote I've always really liked, and the part that I really think is very representative of how the computational science community evolved, is that when you have this lack of reward process for developing collaboratively developing tools and libraries and valuing that process, you have a good reason to expect that you'll have an overproduction of independent scientific software packages and an underproduction of collaborative projects in which later academics build on the work of earlier ones. What that translates to is you are in a scenario where nobody gets credit, like tenure credit, for example, or promotion credit for developing or contributing to a library or a scientific software package. You are going to continuously have, the postdoc who's just going to be like, I have to solve this problem, I'm going to go write the code and get it done. You're going to continuously have the model of somebody who, is sitting there thinking, I want to ask this question and I want to get it done and I don't want to have to there's good reason to not necessarily want to spend 6 months trying to build a collaboration, figuring out how to use somebody else's tool for it. I think I can write that tonight and run something, and whether or not I have good practices for it. This is really what I would describe as the predominant model for scientific code, at least in the United States, to now. And it's the positive side to this is that it is improving. Actually, for the first time, I see universities who are considering, well, can I hire a team of people whose sole purpose it is to help my professors and their research teams develop scientific applications? And it's not a crazy idea. Universities have been doing this for years. They've been hiring, for example, machinists to help their experimentalists build their experiments in their labs, right? But the idea of doing that, right, and providing a career and sort of a place and a value in the academic infrastructure for that development has been a really hard-fought battle. And the reason I bring it up is because the most common conversation that I have with teams that are using our facility, that I have with teams who are considering, hey, how might we implement good software practices, is the cultural battle that they're facing in doing that. The cultural battle with both their team and the cultural battle with their university. And it's important to recognize it. Frankly, as I said, this is cultural, and this is the psychology of humans, right? So there's no clear-cut answer here. But it's to say that this is a good opportunity to talk to your fellow students, talk to your lecturers today about this, right? And plan on the revolution to force people to rethink this. And also to find these, at your institutions, right? If you're at universities, look to see if your university is considering doing things like this and backing it and supporting it, and trying to get your coworkers to also support it, right? Because there's a lot of value here. So some challenges, right? This is sort of just sort of listing some of these things off. Is that on the sociological side, is that you have competing priorities, right? If you're not given tenure credit, if you're not given job credit, right, and promotion credit, more like in the Department of Energy labs, it's hard to value that, right? Somebody has to value that you're contributing to the validation effort or the continuous integration, which we'll talk about later today on an application for it to go forward. I will say one of the exciting things, right, that's very different today than it was 5 years ago is that there are actually applications that are funded to do some of this, right? 5 years ago, I could have counted on my hand, and I did, how many projects were actually funded to care about some software practices in developing their applications. And that's much bigger now. In part, the Exascale Computing Program is doing that, but also other funding agencies are beginning to value that. And that's the start of it, right? When the funding agencies are actually saying we care about this, then change can happen. But limited resources is another really huge one, and as I said, I've commented on it, right? So not everyone has a 5-person code team to make their code bulletproof. And it's not expected that everybody has to have that to write a good scientific code. But then as soon as you're looking at half a person versus 10 people versus 5 people, coming up with what's the highest priority given your science drivers, right? Given the things that you guys are trying to accomplish, and you have to make sort of some informed choices here, and today hopefully you'll figure out how to make those informed choices. The perception of overhead without benefit, right, is a huge one. It's related to this just cultural issue, right? Why would I I'll choose, why would I put my code under version control? I have it on my laptop, it's fine. I occasionally tar it and bring it somewhere else, right? And all you're doing is asking me, to get completely learn something new for the next 2 hours. And this is a really comic example because this is one that I feel like everybody has adopted, like now. But at the beginning of the training program 6 years ago, no, it was mostly, we're still fighting it. But you laugh, but it's really true, right? The idea of just figuring out how to use any version controls, it doesn't matter, right? It doesn't matter which one you use. It doesn't matter if you use the most popular one today. It doesn't matter to anything, just anything. People resist it, right? Because it's that challenge of like 6 hours to learn something new versus like, I'm just gonna keep tarring, I know what that is. There's no energy barrier there. And the other component of this, right, which is real and I think the hardest one, is that especially as codes get more complex, they benefit from interdisciplinary collaboration. It's really useful to go talk. I think scientists in general, like computational scientists, are a little bit more used to talking to, say, applied mathematicians and sort of certain flavors of applied mathematicians anyway, and in terms of improving their mathematical model. But actually crossing disciplines and being able to communicate well and effectively in a way that you might even be able to communicate and collaborate on developing that code, it's just hard. We all learn a very specialized language in whatever domain we're in. We do. And that becomes hard itself to jump across. But then we also learn our own, even beyond that, right, we learn our own way of writing code, right? If you've been working on your own writing code, you write code your way. If you've been working with a team, you write code probably the way that team writes code. And switching to communicate with another team that does it all completely different. Oddly, that's a huge barrier, right? Like it's a really huge one. I want to adopt this library. It has a solver that I could really use. It could really do a good thing for me and for them, right? They want a user. But oh my God, the code, how do we make it talk? And sometimes people just throw up their hands and say, we don't want to spend the overhead on that and figuring it out. I encourage you to consider again sort of the consequences of your choices when you do these. When you're thinking about these sociological issues, especially this interdisciplinary interaction one, about that investment in front to save a lot of time later. And that's all that this translates to. I was talking more about the sociological ones, but the lead into really a lot of the other components of today is to acknowledge that engineering practices on scientific code is not what Google implements. It is not what industry implements. And it can't be. Now, there are some companies that actually do have components of their software base that is under research or under aggressive development at all times. But we have generally found that scientific applications are really their own beasts for many of the reasons we've already talked about in terms of funding and priorities and our own training. But in the end, almost all components of a scientific code are constantly under research, right? And so what does that mean, right? The science itself, like your physical models, what ones you have to incorporate into your code, whether you're incorporating them correctly, all of those components, right, are constantly under research. But often so is maybe the best way to actually write those physical models, the best way to get performance on those physical models, the right way to get performance on any of the particular machines you're trying to use. And that is actually genuinely your research question, right? How to take like a particular set of models in a particular code, right, and optimize that for a variety of architectures is its own career and its own challenging question. So that creates different assumptions in our practices. So we were definitely not trying to say take Google's practices and bring them forward to the scientific community. That does not go swimmingly. We'll put it that way. The other thing is that our requirements change really quickly. And this is another big difference, right? So we don't necessarily have, I'm going to trivialize industry a little bit, right? We don't necessarily have a target, right? Deliver product on day X, period, that's it, go. As I said, I'm trivializing a little bit. But in the process of developing an application with all parts under research, it all shifts underneath you as you're going, right? You might realize that something isn't working and you have to completely change direction, right? It's very dynamic. And on top of that, right, the process of verifying that your code is doing the right thing, that it's representing your physical world, whatever aspect of the physical world you're trying to represent that is doing that correctly, that you're verifying it correctly, that's complicated, right? It's not just even a straight up question of your mathematical model. It's an interesting overlay of the numerics and the mathematical model and moving forward. And the short version of this, right, is this last point, that the real world is messy, the real science world is messy, and so is the code. So how do we deal with that? All right. Okay, so this is sort of a very high-level sense. I want to talk a little bit about life cycles of scientific applications. It's a very high-level description, and I mostly want you just to be aware of thinking about it, that your code, it doesn't matter how isolated to your laptop and your own creation this code is, or whether it's a big collaborative process, all codes have a life cycle and have a process involved in it. And so thinking about this life cycle, thinking about this process for like 10 minutes can actually, one, be sort of kind of an interesting exercise if you haven't done it before, but also help you think about how you want to prioritize what parts of the software engineering process there are. 1 second, I just need a... So, this is sort of hearkening back, but I just wanted to point out that you can sort of reference these later. The short part of all of these is that as you're thinking about the life cycle, as you're thinking about the software processes and how you customize them, is that you're thinking about Agile ways to deal with these things, right? That you're thinking, and buzzword or not, right? That you're thinking, just use Agile as like the lowercase a, right? Flexible, quick changing ways that you can deal with it because, as I said, rarely is the process in scientific code linear. All right, so there's first the life cycle of a scientific application, right? And this is, I think, as I said, this is almost cartoonish, right? Because you start with some science problem that you're trying to tackle, right? The physical world, whatever it is, right? You're studying turbulence, or you're studying cosmology, or you're studying how a nuclear reactor works, or whatever, right? And you've got that problem. And this is exactly the stuff that we're all trained in, right? That you start from there, and you've got some math that sort of represents the components that you care about. So you go into the model, into the equations, and in whatever flavor it is, right? This is a little dated to some degree, right? But this was driven by a particular type of problem. So then you move from the equations into actual numerical solvers, right? Like how do you take those codes, right? Take that model and put it into code. Then you implement it. But the valuable part here, I think, to think about, right, is this sort of what's happening in the middle, right? So first, you do this implementation and you do some validation, right? And just remember, validation is, can be as complicated as nightly tests where you're comparing it against, a huge body of experimental data, or it can be, you're developing the code, you run it, and you do some sanity checks on it, right? So it kind of be both of those things. But in the process of development, right, it's anything in that category. But you go through this process, right, of evaluating the quality of the model, right, and maybe doing iterations on changing there, the fidelity of the model, and the stability of what you've implemented, right? And this is just sort of the standard development, right, of a scientific application. It doesn't really matter, right? In the sense of I was talking about this being dated, right? You could put the exact same thing up here if you had an entirely learning-based approach, right, to how you were trying to tackle your problem. It just put different words, right? It's all the same thing. It's this idea of starting with your physical world, starting with your model, and going through in this continuous testing process. You do this, right? Because I really doubt many people, despite my attacking of the way that we've done scientific process, have just written code, compiled it, and then boom, without doing anything else, run a simulation or run some analysis based on it. You always do some process of this, right? So think about this more specifically for your applications, right? And thinking about that overlapped with what a software productivity cycle, yeah, that's a mouthful, kind of looks like. But in the end, right, it's sort of even a higher level version of what we were talking about in the previous slide, which is that you have your question that you're trying to tackle. You design your experiment that you want to use to answer those questions. And then you sort of start through this model in software development, testing and verification. You run some simulation. You run some analysis. In this case, it could be analysis, not just simulation. You run validation, and you sort of go through that whole cycle, right? And you design a new experiment given what you have coming out of experimental design. The valuable part of this to think about is that these tend to map to different parts of the larger software infrastructure that you're also developing. So I have talked a little myopically, about your scientific application today. And what does your scientific application mean? 10 years ago, it meant something really clear. 10 years ago, it meant the simulation software that you were writing to represent some part of the physical world. Now your scientific application, though, I suspect, might mean that, but it could also mean your workflow. So it could be that your scientific question does not require a campaign. It requires 100 million different runs of something or other, right? And you better have a really good piece of workflow software to help manage that. So I'm not trying to leave behind sort of other components of software that you as a team that you or your team might be developing. All need the same components, right? Of practice, right, to make sure they're doing what you think they're going to do. If you think workflow software is not prone to major errors that will mess you up, I promise you're wrong. I absolutely promise you that you're wrong. And when you're trying to debug something that's even trying to run 1,000 different jobs and you're not really sure where the problem is, it's a lot of coffee and stress. And I'm pretty sure I have gray hairs from some of those. So just keep in mind that there are these abstractions sort of help you think about where you are in your process, right? Like that if you're getting lost about, well, what do I have to worry about now? What practice should I have a practice here that matters? Think about where you are, sort of stop, think about where you are in even trying to answer your scientific question. Okay. And so this is sort of leading into what I would say are sort of the baseline best practices to think about. Meaning that if you have to start somewhere, these are probably the key ones you want to think about folding into your development practice, folding into your team. But again, keeping in mind that these things can be very customizable. So, and in 4 words, invest in an extensible code design, I wrap up a lot. A lot of very complicated topics, all in one fell swoop. All that means is first, have something that might look like an architecture to your code. That's kind of all that means, right? And what does architecture to your code mean? Some pattern, right? Like some design component, some way that somebody could look and say, okay, I'm in like, a low-level kernel that's about to be thrown off to an accelerator, or I am, in a high level, component of where, I'm just trying to maybe figuring out like what the driver for what the scientific application is. Some architecture. And in that architecture, once you have something, right, even if it's just naming conventions, right, this does not need to be complicated, right? This does not need to be go away and consult with an expert in code architecture. It could just be naming conventions of your routine so you know where you are. It could be good documentation a little bit beyond that, right? Sort of, good commenting within your application. So this doesn't have to be super complicated. But an extensible code design can also mean that you've done a job at differentiating concerns, right? So that for example, your parallelism, the things that you're going to throw then and to be, moved off node are written separately from your low-level kernels, right? That you've separated these concerns and built your code in such a way that when, oh, wow, all right, I need to rewrite this kernel for a completely different kind of accelerator, you don't have to go rewrite 1,000 lines of code because it's embedded and, in this larger routine with a lot of assumptions. Instead, it's, 100 lines right there, and you can go work on it. That won't solve everything, right? But a good architecture allows you to understand where you are, allows other people to use your code and understand what's going on, and allows you to be a lot more dexterous, right? So going back to the Agile even with a little a, right? When you know where you are and what your code is doing, and you don't have to go back and sort of remember what you were doing while you were drinking that beer on the Friday night, and that will help, right? So consider that. Like I said before, Just any, it doesn't have to be Git, it doesn't have to be, just any version control. As I said, this is the phase shift where the community is changing. This was something we had to say 5 years ago, over and over again, and most people are doing this now. But also automated testing. And this is a harder one, right, for many people. It doesn't have to be, 100 hours of testing every single night, which is not possible. But some regular testing of your application that gives you some confidence in at least primary components of it, right? Getting into the habit of implementing that. So that could even, at the beginning, that could even just be that you take on Friday morning, you take 5 minutes, right, to set up like 5 problems and submit them and just make sure they're still doing what they were doing, 4 days ago or something, right? It can even be as simple as that, although there's a lot of tools and infrastructure to also help you do that, so you don't have to do that manually. And this goes back to the verification and validation regime. So I would argue, without a doubt, right, as scientists, you need to have rigorous verification. Your code needs to be representing the physical world in the way that you want it to be representing the physical world. If you can't prove that, right, then for example, you probably won't get time on a large-scale system. And we look for that, right? So that's really crucial. But the validation, right, is also really crucial. And the way I like to differentiate those is for the validation, are you still getting 4 when you add 2 and 2? That's the simplest way to think about validation, right? So make sure that you're getting 4s everywhere you expect. Going back to the extensible code design, right, is have coding and testing standards. So what does that mean? And because they're 2 different things. The first one is the coding standard. It's related to the architecture. So if you are even working by yourself, I say this very strongly because I'm not, this is your own self-discipline, but it's really important if it's not by yourself, but even by yourself, just set up some patterns for how you do things, right? How do you label your functions, right? How do you name them? How do you name your data structures, right? Just things like that, right? So that you can have some consistency. What's a constant, what's not, right? What's a pointer, what's not? Things like that, right? Don't obfuscate your code. And they don't have to be complex. This is a sociological one too, right? If you're going to go start dealing with other developers and it's not just you at your laptop, you do have to come to an agreement on what those are. But have that. I can't tell you how much time that will save you, just having the pattern for how you write that code. And it will become, after a time, pretty automatic, right? It's not going to be hey, you're trying to remember, how did I want to label that data structure? You'll just remember, right? But also the testing standards. And so what that means is that if you are in a group especially, right, but even on your own, if you're developing a new component for that code, you have expectations for what you do for testing. So you can say to somebody, when you've put something in the code, I did this, this, and this, and I'm going to return, on whatever testing cycle I have, right? And I know exactly how that unit that I've created can be tested, both maybe as an integrated component of a larger application, but also on its own as a unit test. Though again, I just point out these sound complicated, but they don't need to be, right? That can be, you have written this unit, you've done 5 relevant tests, right, as you were developing it, and you document that you did those tests and what results you got. And then you have some way, right, even if it's repeating those 5 tests a week later, just that you have some component to do that and you document it, right? You can get really creative and complicated and very in-depth, but just start simple. And the other sort of component that's important, right, are clear policies for how you collaborate and incorporate other aspects of code, right? So how you distribute it, how you document it, right? Don't make the assumption that you will just write good documentation tomorrow. Nobody ever did that. Have a process to make yourself do it, and remember, it really. I'd say after 25 years, it saves a lot of time. When as much as my memory might be failing at 45, right, and things I thought would be easy to remember are sort of getting harder and harder to remember, even at 25 and 30, I remember thinking that it's going to be obvious why I did that. Yeah, it wasn't. Let's put it that way later on. Some other things to consider, right, and these are good terms to remember too follow-up and research on your own, is provenance and reproducibility. I would say that even the reproducibility topic is one that is really in the forefront today and is probably very quickly moving straight into the baseline. And what that means is that you ran your code today, you got a result from it, you published your paper on it, and in 3 years, can you reproduce that result? Do you have the appropriate trail of information to do that? It's hard. It's not an easy problem. It's not an easy problem, especially because you might actually have the code, but then there's a compiler issue. Compilers will give you different answers, right? And the architecture issue and floating point roundoff and all of these things, right? But doing the best that you can to control it is really important. And so this idea of reproducibility, keep that in mind. Provenance is also important, right? So the provenance is correlated, right? So understanding that this version of the code in this data set, right, gave me these results, which resulted in this paper, right? Understanding that whole trail is very important and is necessary for reproducibility. The lifecycle management and open development, these are all issues, right? Especially if you're thinking about, well, how can I share my code? How can I distribute this code? How can I move into sort of some code that's production, right? That people can just take and run science problems with, that I can take and run science problems with, versus this is the code that I'm currently developing, right, for something new in the future. And so to think about what that looks like. Sometimes it just takes consciously acknowledging this is the code that's blessed and ready to go, and this is the code that I need to keep working on. So it's as simple as that. And there are resources. I won't walk through these. There's a lot of different references in the slide set. And very quickly, because I'm running long, what I wanted to point out, and you can look at these and sort of think about them on your own and ask questions over the course of the day, are community codes. We used to actually do a whole deep dive, really, into community codes. But I think community codes take all of these issues we've been talking about today, about software practices and community and sociology, and collapse them all into one really big bundle and say, deal with it. But they're also really powerful. So community codes, or even other pieces of the software stack, right? Other things like frameworks and libraries, can do a huge amount to make you as scientists more productive, right? So what does that mean? It can mean that you can sort of, hey, maybe not worry about the most efficient way to implement an I/O solution for your data. Some people really want to do that. That's their job, and they really enjoy that. But not everybody really wants to spend 3 months doing that and doing that effectively, right? So frameworks, community codes, things like that, they can help you tackle that problem, okay? So they're valuable ones to look at. They're valuable ones to consider. I will just say, sort of in closing about this, right, and not spending as much time on it, to realize, though, that when you do that, you also take on a risk, right? It is a community code, or it is a piece of software being supported by this particular funding agency. And so you have to consider that if you are 100% invested in that particular piece of software, what's your recourse if development on that stalls? Or do you have the ability to tackle components of that, right, if they're not prioritized for you? And this happens, right, where the community be like, well, no, we're working on this, but you're trying to work on that, and you have to do your own thing. They're incredibly valuable. They can make you more productive, but there's a risk. And that's all I sort of really wanted to bring forward there. All right. So really, in conclusion, the very first slide I showed with those 2 lines is the conclusion of this, right? That you need good software practices. You need to have them for good scientific process. So think about them. We're going to walk through how to do many of these today. Dig in to the presenters you'll have today and sort of figure out how they've made those work and how they've seen them work in other groups. You're going to need more of this, right? It is more necessary today than it was even 5 years ago, and certainly more than 10 years ago, because of how much more complex the science questions people are asking are, and because of how much more complexity there is in the systems. And I mean, I say this even like looking at the problems coming through at our facility, right? The science questions are more complicated. They are more interesting. They are, they're huger, right? They're just absolutely huge. But as a result, there's an overhead that comes with that of really making sure you can manage that code and understand your experimental apparatus. So think of this as your experimental apparatus. Treat it that way. Treat it with care and a little bit of love. and good luck. Right. Any questions? I know I went long, so yeah.
So I wondered about the issue of programming languages.
Yeah.
Because part of the people are holding onto their language and their codes, and the other half, or fraction, are constantly rewriting their codes.
Yeah.
So I was wondering, how do we have a scientific community come together in a certain sense
and to sort of communicate on how to write the codes, or like what programming languages we should use?
Well, I'm just thinking in terms of like you have N languages, and then somebody comes along and has
N plus one.
One language to rule them all,
Yeah.
and then go
Well,
N plus one at the end.
So I'll give you a little bit of a tangential answer to that. So one, I am really opposed generally to a single programming model solution for anything, right? The one programming model to rule them all that does is freak me out, right? So from a verification and validation standpoint, oh my God. in much the same way that occasionally things are brought to us and said, yeah, I've only ever run this on one compiler ever. That makes me also very nervous. So from that perspective, I get very nervous about the idea of one to rule them all. I am also very nervous about the idea of the programming models that we have today. Not necessarily that I think there's anything wrong with Fortran, because I actually love Fortran. And if you want a domain-specific language, right, that tackles math, there's Fortran. And it's not C++, right? But there's also C++, which a lot of people are writing, and especially because there's a lot more support for them. But the problem is, right, that C++ does not lend itself super well to scientific applications, although it's getting better, right? And Fortran, like, it's basically the Department of Energy and some other components of the scientific community use Fortran. And that's it. And that's it, right? And that is often really hard to maintain, I can tell you, just from keeping vendors interested. So there is a need, right, for improved collaboration on finding how we're going to write applications in the future. I am also a skeptic, and maybe almost even conservative, although I rarely use that word to describe myself, but in this case kind of conservative, that like the wholesale change into a new programming language model seems really unlikely, right? It's going to be sort of a more incremental change, right? It's going to be much more evolutionary and not, sort of this big thing. So whatever comes in, right, that might actually be a good, effective solution to improve productivity for scientists, I think is going to be like one of these things that starts small, right? That starts as some sort of even more library infrastructure, right? But the other component to this is it has to stand the test of all of you guys, right? Like, really, right? Like, there have been dozens of solutions for the programming model to rule them all. And the library, that would be awesome, right? But they have to go through all the scientists, right? And actually be useful. So I didn't quite answer your question because I think it's a really difficult one, but those are just my thoughts on it. And as I've watched, things not be adopted over and over again.
So just a quick follow-up in terms of like, NVIDIA has CUDA and AMD has some, ROCm and then all kinds of different languages in the industry, so how does that?
So that's a much more complicated one, and so this gets into this issue of even technical debt, right? So there's your programming language and your programming model, but there's also how are you writing for an architecture, right? So if you want to write for an accelerator, how are you writing for that accelerator? And boy, are we in a fun time. This is a lot like there was a period of, so I'm not going to directly answer your question. I'm going to use it by analogy. This is my skill now. But when I started writing scientific code, right, in the early 90s, then it was a battle between implementations of MPI or message passing, right? There were 3 big players and some other smaller ones. And actually, the one that won out was not the one that actually had the most pervasive adoption in all of the scientific communities. It was the one that the vendors decided to say, yeah, that one. We can take that one. That one has a standard that we can get behind, and whatever, I was probably other reasons too, right? But that's the one we're going to take, and we're going to make that available and performant on our system. And that's why you have MPI today. Right, and I mean, they were all sort of similar beasts, so it's not like, they adopted something evil just to make our lives awful, right? But they were all very similar, but that's why we have PVM. Sorry, that's funny, that's why we have MPI today and not like PVM. Hiccup. overall, it's a more complicated situation today because for accelerators, we're being told, write with this proprietary one. No, write for this proprietary one. No, it's also write for this proprietary one. That's fun. Over and over again, right? So that's the part where we're trying to take some action in the Department of Energy so that there's less emphasis on the necessity to write in CUDA and be locked into NVIDIA GPUs, for example, or write NIP and be locked into AMD GPUs. And we're trying to sort of push that a little bit to the point that I can say, go look at this solution. I can't tell you that today because we're still figuring out what that solution is, but we're working very, very hard on it. From Argonne's perspective, this is really important to us. We're not going to have NVIDIA GPUs. And Oak Ridge isn't going to have NVIDIA GPUs. And look at all this CUDA code. So we care a lot about it. We are working on it, and it's one of those ones that we are likely to actually deliver something on because we have to. That's my non-answer.
And I want to say that whatever we are talking about throughout the day today is partially to help you design your software in a way where a specific programming model doesn't become your critical point of failure.
Yeah. What I didn't say in all of this, right, is like one of the things we're pushing, right, is at least OpenMP allows this some dexterity, right, in what you're doing, but will it actually give everybody what they want? We don't know that either. But it allows at least potentially some dexterity. I don't know who had their hands up first, but.
Catherine, can we postpone the questions because we are like 20 minutes behind?
This is my bad.
Yeah.
Okay. I will stay. I will not be leaving anywhere.